Okay, thank you. So I was trying to correct an embarrassing typo. I was in denial. Today is not a working day in Denmark. So when I had to write the date, I wrote 3rd of May instead of 1st of May. It's my inner self that was reacting to this happening. Yeah. All right. So I would like to thank all the organizers. As Bert was saying, it's been a lot of work for many people involved. There's been a lot of very good interaction, and it was such an honor to be part of it. I learned a lot, and I hope I contributed also a little bit. I organized 2 tracks mainly on future electricity market and analytics and forecasting, and so I'm going to talk about the second one mainly, that was co-organized with EDF, Yannick Good at EDF. Right, so when it comes to analytics and forecasting, I can just give you the key messages right away. There's quite a lot of interesting topics for mathematicians. I guess you knew about that since we're here today. Then there's a lot of new data streams that are super interesting for us. I will discuss remote sensing, but there's a few others. There's also the fact that we move towards probabilistic aspects, and I'm sure most of you in the room are convinced about that. And then another point is about business models, but in a broad sense. The way we consider the future of forecasting, we're talking about 2050, today managing a next generation energy system. The way we think of forecasting, I think it's going to change a lot. We may move towards more, say, it's a public good, or we may go towards data markets. So I'll discuss also this idea of data markets. But first of all, so I come from Denmark, and I think Denmark is a very nice country when it comes to thinking of next generation energy systems. We want to be 100% renewable based, and we already have so many hours throughout the year where we have more production from renewables than we actually need. I cheated a little bit with this one. If you look at the time up there, it's 2:30, so it's the night, but to my defense, I was in Australia when I took this snapshot, so for me it was the day. Here, if you look at these numbers, that's the situation exactly at that time in Denmark. There is actually more production from the wind turbines than electricity consumption. There's also some plants that are on for some reliability issues, safety issues. But overall, we may be able today to actually run the power system with more wind than what we need, and also putting these plants to 0. So that's really next generation energy systems. Again, we're cheating a little bit. Denmark is one of the best interconnected countries in the world, so that helps a lot. But still, we're going there. Right, so when it comes to renewables in electricity market and power systems operation, there's this picture of the system here in the middle, and then there's this picture of the market on top. So most of us here have maybe a preference working with the systems or working with the markets, but still at the end of the day, it's everything together, and renewables are just impacting all of that. There are lots of problems, decision-making problems that will involve renewables and forecasting, and I think some of us have been working on these problems. There's classic papers that are highly cited about reserve requirements from Ireland. There's classic papers about unique commitment and economic dispatch. Shmuel had a paper with Anthony Pavarasiliou in OR, for instance, in terms of how to rethink that if we have trajectories and do it network constrained multi-stage. Storage is really high, so there's so many papers about coordination with storage. Trading, we heard about trading just now, so you can imagine we need forecast. And maintenance planning, we'll also hear a bit later today. Right, so there's so many problems, and I think it's recognized today that all this analytics and forecasting is key to the integration of renewables. We really need that, and it's actually not that straightforward. In 2014, the MIT Technology Review actually listed it as one of the 10 breakthroughs, next to microscale 3D printing, genome editing, brain mapping, etc. So that's really a pleasure to see that, first of all. And I think it's really true still today. The development out there in industry and commercial providers are really advanced, but there's still a need for a lot of work from mathematicians, engineers, etc. to help develop that. So we're going to go through that, and it's linked to what we discuss in our research track. I'll start with viability and uncertainty, which are the key issues there, where we are coming from and the status quo, and then we'll develop into this perspective that I mentioned. So this is Hornsrev. Hornsrev is the first large-scale offshore wind farm that was ever built, 160 megawatt, west coast of Denmark. And if there are two reasons why I moved and settled in Denmark, one is my wife and family, and second is this wind farm. When I was offered a position at DTU, I was going to be one of the first in the world and one of the only in the world to be given the data from this wind farm. 1 second measurement for each and every turbine, all the weather measurements around, etc., etc. This is really a treasure if you want to do data science. We have to say data science these days. We would say statistics at the time. But I'm not kidding. This is really one of the reasons why I settled in Denmark in the first place. Right, when you look at the data from such a wind farm, we have wind speed measurements. So that would be here an episode of 5 days with wind speed measurements. And after you convert through the power curve of the wind farm, this is what you see. So already looking at the wind speeds, you can see that there are some periods with some crazy fluctuations. You have some periods with some, let's say, medium nice fluctuations. And you might have some periods that are actually super smooth, right? So that's offshore or near coastal meteorology for you. And then when we convert to power production, just focus on this nasty period here and look at this kind of swings. Within 10 minutes, it's almost going from max production to nearly zero and up to back to nominal capacity of the wind farm, right? It's just crazy in terms of power output. And when you have to integrate that in the power system, that can create a lot of issues. So I come from Denmark. I'm going to talk about wind mainly, but if you look at data from solar power production, you will see the same kind of things with cloud passages. In Australia, for instance, they publish a lot of data from different campuses with solar panels. So you can just go and load the data yourself. It's 1 minute resolution, and you will see some crazy stuff also there, right? Okay, so if you think of this data for offshore wind farm, it's very interesting, very important for the control of the wind farm's output, for the balancing of power generation, etc. But there's also nice mathematical challenges in the modeling of this kind of fluctuation. I focus more on the short term, on operational problems, but I know that Chris should give a talk on looking forward in the future, and Amy is there also, so you're going to have some discussions about that. And there's been in the wind community a lot of discussion over the last 20 years related to the fact that when we assume that we can estimate this mean wind speed, you know, that's the resource assessment, that's just that, right? But actually, if you look at these long records of wind speed you can get, for instance, in the Netherlands, so this is for Schiphol Airport, there's a high variability. This is just the average, the mean wind speed over the year, each point, for each and every year from 1950 to 2005, right? So when the mean wind speed is at 4.7 at 6.5, you can imagine that if you start developing the time series, they really don't look alike. I mean, this mean difference has a high impact on all the higher order moments of the stochastic processes. So it's not just about the short term, we also have to consider what's happening at different type of time scales. I remove a slide. We have a colleague who is called Robert Votard in France. He had a paper published in Nature, Geoscience, also on the very long term. And actually, can we know how wind speed is going to develop if you look 50 years ahead or 30 years ahead even? So there's all these kind of time scales we need to consider, but I'll focus more on short term and operations. So where are we coming from? If you looked at the literature 20 years ago, and if you still look at commercial offering today for quite many, what people do is that they focus on a single wind farm, on a single solar power plant. And they do amazing stuff, don't get me wrong. They get weather forecasts, they do a bit of computational fluid dynamics, they model the wind fields all around the wind farm, or that can be for solar irradiance if it's a solar plant. Then they have some very nice statistical modeling, they look at the conversions, shadowing effects, etc., etc. And eventually, they make this kind of forecast where they have a single trajectory in the future for the next, say, 48 hours, hourly resolution. And this red line is the conditional expectation. So that's kind of the mean of what could happen given the information at that time my model, my parameter estimate. All right? So this can look, in green here you have the observations. This can look very good, this can look very bad, depends on the situation. But people would do that with wind farms one by one. That's very nice. But how many wind farms do we have around these days? It starts to be a bit of a lot of work. So it's a lot of work if we have to look at each site individually, even if you do amazing things, but also we are missing on opportunities. So what people starting doing, so maybe first in Denmark and also in other places, is say, okay, but then these wind farms, and that can be solar power plants, they are sensors. They're not just producing. I'm also sensing the weather through some kind of nonlinear transformation that's called a power curve, right? But if you were to start integrating all this data in some models, you can actually improve a lot the forecast. Obviously, you have to think about the weather dynamics, the fact that Denmark is a tiny country. So when you have a weather front passing over Denmark, it's just coming and then it's gone, right? It's just that quick. So for us, we could look at improvements over 2 to 5 hours, kind of timescales over the whole country, and we would observe these are improvements in terms of RMSE, root mean square error. We would really verify this kind of thing. Since wind comes mainly from west in Denmark, these wind farms would act as sensors, and most of the improvements are on the east side of Denmark. And you can do that in many other areas. You see these kind of things. We had data from Australia where we looked at that, etc., etc. All right, so that looks very interesting, but that's just Denmark. That's very small. And in terms of modeling, for instance, this paper that showed this result, it's very simplistic. Today, we can go to very advanced formulation, very advanced problems. You can consider SPDEs if you want to look at random fields and have this kind of process where we look at the large scale and much more complex features. All right, there's another thing. There's a lot of new data that's coming into the picture. We get lots of data from these wind farms, but maybe what we learned from our colleagues from solar energy is that there's so much from remote sensing. So if you know people who work with solar energy, they're obsessed with these sky images, even throwing your iPhones and collecting pictures from an iPhone and using that for cloud modeling. In the wind satellite images also, in the wind community, it's a bit more tricky for several reasons. But still, from the year 2009-2010, we got money in Denmark where we say, okay, we're going to install some weather radar at an offshore wind farm. That was the first time ever. We used this kind of weather radar you would have at an airport. Then we collected all these images, and then we could try to see if we could use that to better model the wind speed time series and the wind power time series. Okay, so there's a few issues there. First of all, a weather radar is not supposed to survive a storm offshore. So this radar died in the middle of the experiment. And second, we don't really have the skills. We have a lot of friends doing image analysis, etc. But still, when you look at the specific problems, we don't really have the full package of skills to get the best out of these radar images. So there's a lot of reasons why this is going to pick up. You can monitor the weather conditions on site, and the people who operate offshore wind farm will tell you that's key. That's safety or personal on site, right? We can do a lot of work related to meteorology. My colleagues who do meteorology, they love it. It's new data. They are super informative. It's very nice. We can improve the forecast and do better control. And eventually, the way I tricked my colleagues at Ørsted to get this radar in the first place is that they have to do environmental studies and count birds around the offshore wind farms. And this kind of radar is amazing for counting birds because you just have these little stains appearing on the images, you track them, and based on some kind of expert rules, you decide this is a bird, this is 5 birds, this is what they do, etc. So we actually teamed up with the environmentalists to agree that we needed this radar. Okay. Some colleagues, they are called Ørsted now. It was Dong Energy at the time, and Vattenfall did the same. They actually picked up on this idea, partly because of this work and also independently. But there is the first weather radar installed for offshore wind farm purposes in the UK. The project is called Beacon, and it's at Westernmore's Rough wind farm. I mean, it's on the coast. One thing maybe we learned is don't put a weather radar at the wind farm offshore. Keep it on the coast and make sure it can look there, right? So, but this is happening, and that's a lot of very interesting data. One of my former students is working on this project and collecting the data. It's overwhelming how interesting that is. All right, now we move away from the forecasting itself, and some of the things we've been discussing in our research track and that are very important is that forecasts are there for decision making, right? But do we really know well the connection between the forecast and decision making? A lot of people here are experts in decision making, in optimization. Quite a few are experts also in forecasting, but not many of us have been experts at everything together and understanding fully the interface. Forecasters, traders, portfolio managers, and others have different loss functions. Typically, as a forecaster, I'm told you have to optimize, minimize an RMSE, so I have a quadratic loss. None of my clients have a quadratic loss. Over the years, I've talked to them, none of them has a quadratic loss. A trader will have a piecewise linear loss that is that simple if having no kind of backup, or a bit more complicated if having a portfolio, and that's still very simple. If you look at intertemporal constraints, spatial constraints, etc., we might not be able even to draw these loss functions. So what's the best forecast in such a case? Over the year, we've been advocating for probabilistic forecasting. I think people have picked up on that quite a lot. For trajectories, we want space-time scenarios so that we sample the marginals, but we also have the dependent structure in space and in time. So that's the paper of Shmuel and Anthony Papavassiliou, showing that when you use this trajectory as input to multi-stage network constraints, stochastic unique commitment, you do quite a lot more. And then there's quite a lot of these products, you could say, that follow these lines, being probabilistic or giving some information like trajectories. And these days, since there's so much focus on new type of optimization problem, change constraint, robust optimization, we've even been working on defining forecasting product and generating forecasting products that are a bit weird, you could say, but very useful, like polyhedra, ellipsoids, so that you can directly plug that as input to different type of change constraint or robust optimization problems. So these are some of the key challenges we see in the techniques of forecasting. Then we need to scale it up, because if we look at 2050, next generation energy system, we're going to have a lot of those wind farms, a lot of these solar power plants, and the game is going to be very different. You have this open mode community that has been working on developing a data set. We have been working on developing data set. Eventually, we want to work with the full Europe, the full US. You also have data sets for Manuel. There might be other data sets coming up, right? So in the future, we see that we want to predict renewable power generation, maybe load for the whole Europe with all the probabilistic information, dependencies, etc. And if we do all that at once, we have consistent information for agents, which is quite more important than what you may think. If you want them to coordinate, I don't know, you do reserve sharing, and you don't have the same views on uncertainty looking from Germany or from France, right? But you have to agree on reserve sharing. That's going to create issues. So we want to have consistent information here. And we also want to do uncertainty-aware management of the energy system. So that's why we need all this uncertainty information. Right, so quickly, some perspectives. Let's be cheesy for a second, right? I'm allowed to do that. I travel to give this talk, so I'm allowed. So sharing is caring. I work with peer-to-peer markets, so normally I would use that for peer-to-peer markets. But one of the things I really want that we share is data and information, right? And I have reasons for that, and I think quite a few people here in the room would agree. And one person who is not here in the room, I'm going to mention him twice. It's Monter Dahle at MIT. He also agrees, I'm fairly sure. All right, so we started that quite a few years ago with my colleague Jalal Kazempour and someone here who is now a market advisor at ENSOE. Our idea was that Denmark was the first country to push to say we need an overall forecast for wind power generation to be published before market clearing so that all agents have this information. That sounds like a good idea, right? You don't agree? Or you're not sure? Where is he going with that? Okay, so this is a very good idea. You want all agents to have this information. But think of it, just have a bit of perspective. Everybody is just optimize using this information as input. And the forecast is wrong. And we're just all following that, right? What if we start saying, no, I don't think the good idea is that we have this one overall forecast for everybody and everybody optimize versus that, but I incentivize people to share information and mix public and private information, right? So that's where I say Munter and Tsitsiklis and some others have some papers where they look at this kind of idea and look at the equilibria that we get out of it. And do we have increased social welfare? So for electricity market, we've been investigating that, and I think there's a lot more to do there. The other alternative, since people don't want to share data, is to go towards distributed learning. So you don't want to share data with me, but I'm going to split my learning problem and you're going to help me to learn, right? So that's a very good idea, but we wanted to do it privacy preserving, because if I don't want to share my data, I don't want you to be able to write an inverse problem and learn the data I have, right? So that's where also there's quite a lot of work to do. can we do distributed learning in a privacy-preserving way, and that is useful in energy systems, right? So finally, and that's where Monter Dalle has this YouTube video and a paper on archive on this data markets. So that was Princeton Optimization Day last year. You may want to look at it. And so Monter has a very interesting idea that we've also been pursuing that in Denmark. The idea of Monter is that we're going to have this market where we're going to share data for a prediction task. So we simplify it just about a prediction task. But when I start sharing data, actually I add noise. So you have kind of a differential privacy view. You're going to add noise to the data. And depending on the price people are ready to pay, you just lower your noise, right? So you reveal a bit more of what you have. But if you think of it, it's very smart. Because if you do it the other way, how am I going to decide if I want your data if I'm not even sure of the value I can get out of it? And I think that's the key issue with these data markets. We don't really know. The value of the data will depend on your decision problems. But we don't really know that from the other side. So when I want to give my data, I cannot just say the price is that, because it's been tried before, and on the receiving end, no one buys your data, because the idea of the value of the data is not the same than the price tag you've put on it, right? So there's a lot of work in the design of these data markets, and in this matching, you could say. Right, so to conclude, there's a lot of interesting problems for mathematicians just looking at the stochastic processes, nonlinear, bounded, non-stationary. There's a lot of challenges related to high dimensionality and the fact that we have probabilistic forecast. There's also this perspective related to distributed learning and data markets. So if you're keen on this kind of topic, being on the academic side or industry side, I hope you'll get on board. And we also try to publish a few papers following up on our work here. So thank you very much.
Thank you, Pierre. Are there questions?
Yes?
Can you comment a little bit on differences between when you predict stuff on one wind farm versus, on one wind plant versus aggregated wind farm?
Okay.
And what are the benefits from that?
Okay, but so, I mean, at one wind farm, you can imagine there's a lot of local effects, right? So as you start aggregating, you're going to have a better signal-to-noise ratio. And eventually, it's going to asymptote, you know, it's just no more smoothing effect. So a lot of people have been very keen on aggregating a wind farm for that reason. Just we have to see if it's consistent with market operation. As long as we have these kind of zonal markets in Europe, we can think of aggregating. But if we go more towards nodal concepts, then it wouldn't make so much sense anymore, right?
But is there a benefit, let's say, you need less flexibility on the resource side to balance these uncertainties when you aggregate, right? And so there is a lot of benefit in overall longer-term efficiency.
Yeah. Okay, there's one topic I left aside because I was told not too technical. There's one strand of work that's coming now, which is about forecast reconciliation, and it's from Australia, Belgium, Denmark a bit. So the idea is to say that we want to make sure that whatever the granularity, you're consistent, right? And so then that would kick away this idea that you want to focus on a certain granularity level, because with this kind of consistency, you make sure that everybody would just pick the right granularity level and still get the most out of it. So this is not fully come yet, but this is one of the hot topics in energy forecasting. Yeah?
As we move toward more and more renewables, you know, I believe that sooner or later we'll start to treat some of those resources as dispatchable and start to be a little more proactive in terms of changing pitch of blades and things like that. Will that diminish the importance of being so precise in the forecasting by adding controllability to the wind?
Yeah, but so I think it's mainly for solar. There was again yesterday, 2 days ago, an update from ESSIG in the US about dispatchable solar power plants.
Well, both. In wind, you can change the pitch of the blades and modulate some of the output.
Sure. So, I mean, it's still about the original resource. You have the same argument with storage. As we put storage everywhere, do we still need to forecast? Actually, yes, because what we're going to get as input to our storage is still something we need to know about, so as to optimize the strategy for the storage or for pitching, right? So I think in terms of if you're on the system side and market side, you might be less worried about the original forecast, but you will still need the forecast to decide on the pitching and the storing and strategies, in my opinion.
People think of renewables mistakenly as a free marginal value. In fact, wind is not free if you think of the impact on the conventional dispatch. And so adding some control they may actually make it a little more manageable than to just treat it as a free resource that you have to kind of wait for the mana from the sky.
So that goes both ways. Wind is not free, but also there's new opportunities eventually, because as you have more controllability, you also use wind for ancillary services, and you can develop trading strategies for that, right? So it goes both ways.
So two more questions have come up here.
I don't know, maybe you already tried that. There is this European Wind Energy Association, and there is also Energy Commissioner. You could try a pilot with forecast based on 1-2 days wind estimations over Europe.
I mean, I do that already. I worked at ECMWF also myself, so I.
And then I wanted to ask you, since you know this Horns Ref farm very well, when it was built, was it designed to take into account this wake effect? Is it properly designed in terms of this tail?
Okay, so it's actually not the original topic, but it's a very exciting topic. Our knowledge of near coastal meteorology, wind, was not so amazing actually at the time, and this kind of project have helped us to learn a lot more. So there's one of my colleagues, Rebecca Barthelmy, who is at Cornell, for instance. She's been working on that and realized that the kind of wake modeling we were doing were not really correct for this kind of arrays of turbines in near coastal areas, but now we have much better understanding. So this first that's the first Horns Reef wind farm. Now there's two more. The spacing and the design here is not optimal if you think of wake properties in this near coastal area, but now we've learned our lesson. It's like the first wind farms, if you look at the western US in the 80s, you know, some people have not been very smart, but we've learned our lesson. Here it was already much better. The loss were not as bad, but still our knowledge of wakes, especially the long wakes. If you think of the whole wind farm as having a wake and where you're going to put the next wind farm, the recovery length is much longer than what you may think based on the theory that we have.
Sometimes 70 kilometers.
Exactly. But our mistake, we have to put it in the balance. The other wind farms are less than 70 kilometers away. So they are affected.
May I please just make a comment? And all these wind powers will have an impact on the climate.
Yes. So you have this person, Johan Driessen, right, in Belgium, who works on that, and Professor Menneveau. I agree. There's a few papers out there that looks at the impact of wind farms on local and regional climate. We have to be a bit careful. Yes, I agree.
Same for photovoltaic, I think.
I'm not knowledgeable on that. I would think it's worse for wind in the way you extract the energy and have this kind of bubble of wake effects around. But yeah, I agree. They're starting a debate.
Next question.
Okay. I was curious whether you had a look at a spatial correlation structure in such a way that you can link to your general model, right? Depending where the wind local farm is located, and having given a functional for shaping this spatial correlation structure between all points, then your model could be more tailor-made for the
so if you look at the big picture here, so Florentina is asking about spatial correlation structures. If you look at the big picture here, there's a lot about this kind of parametric representation, semi-parametric, and how you're going to play with that. That's why I was mentioning SPDs, because SPDs would be a really good idea to have a lot of flexibility for modeling that.
And Fred Bent, sorry for interrupting, he has something for Norway.
Okay.
Linking with random field and having functionals to model correlation structures.
All right.
In case.
Yeah.
Okay.
Any questions? If not, let's thank Pierre again.